In today's lecture, we're going to cover Chapter 6, Correlational Methods and Statistics. So we've talked about correlations a few times already in this class, and the book defines a correlational design is one that allows us to describe the relationship between two measured variables. So again, a correlation is a statistical technique that measures the degree of relationships between two variables. Typically, we do this with continuous data, so ordinal, interval, and ratio. This allows us to answer the question, what is the relationship between blank and blank? A correlation can tell us two really important things about a relationship between two variables. First, it can tell us the strength of a relationship, so is this relationship weak, moderate, or strong? And it can also tell us the direction of a relationship. So is this relationship positive or negative? Knowing the direction and strength of a given relationship can allow us to make predictions from one variable to another. All right, so correlations help us with two major goals of scientific research, description and prediction. So why isn't a correlation able to explain behavior? Well, third variables are a key part in answering this question. Let's think about what a correlation does. We measure and observe two variables. Our predictor variable is on the x-axis and our outcome variable is on the y-axis. But that's it. We aren't controlling anything or manipulating any variables. So a correlation can tell us if performance on the two variables correlate. As one changes, do we see a systematic change in the other? So like I said, a correlation can tell us about the direction and the degree of a relationship. But how do we come to know that? Well, the direction of a relationship will be either positive or negative. The magnitude will be a value ranging from negative 1.00 to positive 1.00. Stronger relationships are closer to the absolute value of 1, so positive or negative, and weaker relationships are closer to 0. Now the direction of the relationship. For a positive direction of the relationship, increases in x are accompanied by a systematic increase in y. In the same vein, decreases in x are accompanied by a systematic decrease in y. Everything is moving in the same direction. Now, negative relationships can be viewed as inverse relationships. Whoops. Sorry about that. So, negative relationships can be viewed as inverse relationships. Increases in x are accompanied by a systematic decrease in y, or decreases in x are accompanied by a systematic increase in y. And this will make more sense as we begin to actually visualize the data. Which brings us to scatter plots. So, what is a scatter plot and what can it tell us? Well, a scatter plot is a figure that graphically represents the relationship between two variables. Both the x and y axis represent a continuous scale. Each dot in the scatter plot represents a single person's relationship between the two variables. And this overall picture allows us to visually inspect our data and determine if an actual pattern exists. And we're going to take a look at a couple examples. So first we have what is the relationship between ACT and GPA? Well, the table to the left is all of our data, right? And the scatter plot is all of those values plotted visually for us. Now each dot is one person. So if you start with the top column, we have an ACT score of 23 and a GPA of 2. If you lined your finger up on the screen at 23 across the bottom and 2 across the left side, you would end up on one of those dots right there on that line. So see how they are all kind of clustered in one area and you can kind of see a pattern? Well, here you can see that an increase in GPA and an increase in ACT are related. So here we have a positive relationship between ACT and GPA. As GPA increases, so does our ACT score. Now let's take a look at another example. So, what is the relationship between student absences and final grades? So, the more absences you have, the worse your final grade is. So, take a look at the table to the left. You see 0 absences is a 100 final grade, 4 absences is a 76. So, what we see here is an increase in X. So, the more absences you have, is a decrease in Y. So, a lower score in the class. So, again, this is an example of a negative relationship. As one variable, your absences, increases, the other variable, your grade, systematically decreases. All right, so perfect correlations would fall on a straight line. They are like unicorns, something that we talk about a lot in this class, pretty much a theoretical construct. You never have a perfect correlation in real life. So you have to imagine the perfect line and compare your data to it. So see at the top how the dots are more spread out from that imaginary line? That is more of a weak relationship. But the bottom 2 examples, the dots are closer together on that imaginary line, which represents a stronger relationship. So the strength of our correlation is directly related to the tightness of these points along the line. And we're going to take a look at quite a few examples to make sure that you are comfortable with this. So this first example is a perfect positive, just for reference, relationship, right? So that's a perfect positive. The next example is a strong positive. See how clustered those are across or next to that imaginary line? And this is a more moderate or weak positive example. So the dots are quite more dispersed. They're not quite as tight on that imaginary line. Now, this is an example of absolutely no relationship. So the dots are kind of all over the place, and that imaginary line is going to be pretty horizontal, right? This is an example of a moderate or kind of weak negative relationship. So the dots have a negative pattern to them, but they're not very tight across that line. And then that last example is, again, a perfect negative correlation, which we won't see very often, but just for reference. Now, related to correlations is a correlation coefficient. And what can it tell us? Well, a correlation coefficient measures the direction and degree of a linear relationship. And why do we use interval and ratio data for this? Because we need equal unit size. And we transform our raw scores into z-scores, right? So relating ACT and GPA. ACT is typically what? A scale of 0 to 36, where GPA is a scale of 0 to 4. So we transform everything into z-scores so that they're comparable. So here's the formula for computing a Pearson-R correlation. And we aren't doing this by hand, but just so you're aware of how they're calculated, I wanted to throw this up here. You calculate the cross product of each person's z-score, so multiple z-scores for ACT and a score for GPA. Then you sum all the cross products, divide by the number of pairs, and you get a Pearson product correlation. So if you had 30 participants who each reported GPA and ACT, you'd have 30 pairs of GPA and ACT scores that you would use to calculate this coefficient. So basically our formula is explaining that this correlation is a value, right? Based on the degree in which the values of X and Y are scattered around their respective means. So we have to take the mean into consideration. A correlation value tells you if paired scores occupy the same relative position within their own distribution. So if you looked at the two distributions together, how do they compare? And I know that sounds really confusing at first, but hopefully you'll get a better idea of what that looks like as we go through these next few slides. So a little more on Pearson correlation values. You will need to know this. So a high positive relationship is when both z-scores are high and they are both positive or both negative. A high negative relationship is both z-scores are high and one is positive and one is negative. And no relationship would be positive and negative values of your z-scores that cancel each other out. All right, so I always like to relate the math that we do in this class back to the writing and publication process, which is something that we've grown to understand is very important in this class. So imagine that you're reading an article and you've been given information on the data's central tendency, its variability, its shape, the things we just did in Lab 2. And then you come across this. There was a significant positive correlation between the amount of sleep and exam scores. R equals positive 0.73, N equals 30, and P is less than 0.05. The more a person slept the night before, the higher their exam score. So if you had all of that information, your central tendency, variability, your shape, and information on the correlation of the data, you'd really start to get an idea of what this data looks like and the story that it's trying to tell. Now, these are the typical cutoff points on how to interpret a Pearson R correlation. So you'll hear them referred to sometimes as t-shirt sizes. So a weak correlation is anything from 0.1 to 0.3. Moderate is 0.4 to 0.5. And strong is 0.6 to a perfect 1. And that's in the positive or negative direction. So let's do some practice. With this first example, we have a positive 0.74. What is this relationship telling us? Well, that's a moderate positive relationship. A negative 0.89, that's a strong negative relationship. A positive 0.03, that's a weak positive relationship. A positive 0.76, a strong positive relationship. A negative 0.22 is a weak negative relationship. A negative 0.51, a moderate negative relationship. And then just for giggles, a positive 1.00 is a perfect positive, and a negative 1.00 is a perfect negative. Now, here are the examples that we looked at a few slides back, but we're going to take a look at the Pearson R values associated with them. So as you can see, the first example has a perfect positive 1.00. The top middle example has a Pearson value of 0.91, so that's a pretty strong positive relationship. The third on the top is a positive 0.56, which is a pretty moderate positive relationship. You can see the bottom left is 0.00. So remember, that's the one where there's no relationship present. The bottom middle is a negative 0.66, so a moderate negative relationship. And the bottom right is a negative 1.00 or a perfect negative relationship. So you can see the variability in all of these scatter plots, how they're related to the Pearson R value, and really get a sense of what the data is trying to tell you. Now, one thing to keep in mind with correlations is that restricted ranges aren't great for correlational data. They tend to weaken them. This is again why it's important to use our z-scores. Then you also want to make sure that you're looking at the standard deviation and any other data that's available. So just remember that you can't just look at a correlational value. You need to look at your data as a whole. All right, so when we first discussed correlations back before exam 1, we talked a good bit about why correlation does not equal causation. This is probably something that you took away from your Gen Psych class and you've heard over and over and over. Well, think about some examples where correlation does not equal causation, right? We have third variables that could always be impacting our two related variables, right? So let's take a look at an example. So this is classic, and I know many of you have probably heard this, but there is a positive relationship between the number of homicides and ice cream sales. Now, we can't say that ice cream sales cause homicides, right? No, what it is here is we have a third variable of summer heat that influences both ice cream sales and the number of homicides. So again, we cannot say that correlation is causation. We can just say that the two things are related because we cannot eliminate third variables. Now, the last thing we're going to cover in this lecture is a regression analysis. So let's talk a little bit more about that. So a correlation lets us describe a relationship, and a regression does too. Plus, we're able to predict the value of one variable given the value of another variable. So the example here is, suppose that you know that ACT and GPA are related. If you know someone has an ACT score of 3.5, you can use that to predict their GPA. So I'm sure that a lot of you remember this formula from other math classes that you've taken, right? So y equals bx plus a. Y at prime, that's that little dash next to y, we say y prime, is the predicted value of y. B is your slope of the line, and A is your y-intercept, so where it crosses on the y-axis. And again, we won't be doing this by hand, but you will need to know what each of these represents for your quizzes and exams so that you can demonstrate an understanding of what the formula is actually showing. So make sure you save this slide. So if we ran a regression, which relationships would best predict y? So take a second and think about that. Well, perfect positive and perfect negative correlations would give us a better prediction of y. The stronger the correlation, the better your prediction will be. So that is our mini lecture on Chapter 6 correlations. If you have any questions about anything that was covered in today's lecture, be sure to reach out to me as soon as possible. We can talk via email or set up a time to meet during office hours. And have a great week.